Hi, everybody. So my name is Andrei Luțaș, and together with Jun Nakajima, we're going to talk about the virtualization-based hardening, security container workloads, and beyond. So very briefly about myself, I've been in the security industry for the past 11 years. Most of my life I've spent doing hypervisors, simulators, and so on, and security for them.
And then my name is Jun Nakajima. I've been attending a KVM from I think the first KVM forum. And actually I attended the first Zen summit back in 2006 kind of thing. So I've been working on virtualization more than 15 years. And actually I wrote the first BT code, BMX code at Intel. So, this is the agenda. We start with VBH. The name of VBH is dry, but it's virtualization-based hardening. Okay, it's very simple. So, and HVI is hypervisor-based introspection. Okay. So first of all, I talk about the VBH. Again, the virtualization-based hardening. So virtualization and then security is it's very closely related. And in other words, we can implement certain security features using virtualization. Okay. In fact, Intel VT was developed initially for security features, actually. So what it means is, by using a hardware feature, virtualization feature, we can implement ring -1, right? Basically, that can even control monitor ring 0 stuff. And by having that hypervisor software component, we can virtualize the physical stuff, like a physical memory, CPU, and then I/O. Okay. That way, we can monitor or isolate and then protect resources. Okay. Then the idea of VVH is actually pretty simple. Compared with the ring 0, just a bare metal, by using virtualization, especially hardware features, we can have more security features, right? Because the virtualization feature was invented for that purpose. And I initially presented VVH 3 years ago, and today we actually have source code, and then that's open, and we'll have the URL for the GitHub. Okay. It basically, what the VVH is, it's a very thin hypervisor, okay? And many of them are pass-through. For example, I/O is pass-through, and the interrupts are pass-through, okay? But it has ability to monitor or isolate or protect some certain resources, okay? What it really does is, today it implemented as a Linux kernel module, and what it does is it deprivileges itself, the Linux itself, deprivilege itself from the next instruction. So it basically VM enter to from the next instruction. Then it becomes kind of guest mode, okay? Then we have a very small thin hypervisor. And VBH itself is just a passive entity. So it doesn't know what kind of events, what policy it needs to do, right? If an event is detected, it doesn't have a knowledge or the code, the policy to handle that event, and it must be given from outside, and that is basically the next one. It's a hypervisor-based introspection, and so then what Andrea is talking.
All right, thank you very much, John. So, like you already mentioned, VBH is the passive infrastructure which provides the virtualization API, which can be leveraged by a security module in order to provide protection. And the best way, in our opinion, to provide virtualization-based protection is by using introspection. So the term of introspection was introduced more than 15 years ago by Garfinkel and Rosenblum. And in a nutshell, it means analyzing, inspecting the state of a virtual machine from outside of it. So more specifically, hypervisor introspection has two main roles. First of all, it has to bridge the semantic gap, right? Because looking at a VM from outside of it, there's not much sense making out of it, right? It's just raw memory pages, which you have to analyze and basically decide what's there. Is it a process? Is it a driver? Is it a code page, a data page, a stack, and so on? So once it leverages and it bridges the semantic gap, HVI can use the virtualization features in order to provide protection for that VM, okay? So in a regular scenario, it can protect kernel and user space from several types of attacks. And in this particular scenario with VBH, we aim to protect a host kernel from potentially malicious containers. So how can we do that? Well, usually HVI uses two main virtualization features. The first one is the EPT, the extended page table, which allows us to override the memory policy enforced by the operating system. So if you have, for example, a memory page which should not be executable, for example, a stack or a heap page, and you mark it inside the EPT as being non-executable, even if an exploit inside the guest operating system manages to somehow get the execute code from that page, it won't be able to get passed through the EPT, right? So HVI using the EPT infrastructure will be able to block such exploits. Similarly, pages which normally should be read-only, for example, code pages or read-only data or some sort of secrets, can be protected from the EPT level by flagging them as being read-only inside the EPT. So even if an exploit manages to abuse some sort of vulnerabilities inside the operating system to attempt to modify those pages, it won't be able to get past EPT. And the second major virtualization infrastructure that HVI uses is the ability to intercept accesses to other resources. And by other resources, I mainly understand registers, so MSRs, control registers, descriptor tables, and so on. And we'll see later that this is pretty important because, first of all, several MSRs contain important values, like the system call target address, and the control registers naturally contain, well, control bits, which are important for the normal behavior and functionality of the guest OS. And more importantly, they contain security-enabling features. For example, supervisory mode execution prevention or supervisory mode access prevention. Okay, so the architecture in a nutshell, like June already mentioned, VBH provides the passive infrastructure. It is a module all by itself. And HVI can be another module. And both of these modules can be loaded inside the Linux kernel. VBH will deprivilege the Linux kernel by enabling VTX on each CPU of the running machine. And HVI will make use of the API VBH provides to analyze and to enforce virtualization-based protection for the Linux kernel. And normally, our architecture involves two main communication pathways between the two modules. First of all, the VBH module will provide the API for the HVI, and HVI will use this API to, for example, modify the access rights for a guest physical page, or to enable VM exits whenever writes take place on a certain MSR. On the other hand, VBH will provide VTX events for HVI. So each time a VM exit takes place due to an EPT violation or a CR register violation and so on, it will make sure it forwards that event to HVI. HVI will get to analyze the event, decide whether it is legitimate or not, and act accordingly. The policies can be loaded inside the HVI in any way the programmer desires. It can be a configuration file, it can be hard-coded inside the HVI module, and so on. Another use case, which is important to us, is the nested version. And luckily, because VBH does not make use of heavy virtualization features, it can run nested pretty well on KVM, for example. And nested scenario is without a very deep performance impact because, like I said, simply using EPT and using basic virtualization VM exits will not incur a significant performance penalty, but it would still allow HVI to leverage all that virtualization power in order to protect the Linux kernel. Now that we have the big picture and the architecture, let's see a few exploits that we were able to mitigate using VBH and a very, very small, very thin layer HVI module, which basically targets individually these types of exploits. So the first one may ring a couple of bells here, is the dirty cow exploit, which abused a race condition inside the Linux kernel, which leads to a misbehavior when handling copy and write on read-only pages. And well, they say that a picture is worth 1,000 words, and we assume that a video is worth 1 billion words, so here it goes. Grab your popcorn. So this is a POC where we use VBH and HVI to prevent the dirty cow. So on the left-hand side, we have your right side. We have Docker, which will run inside of it a dirty cow exploit. On the right side, we simply load the VMX switch driver, and when we run the exploit, we will immediately see several EPT violations being triggered. Now, the important thing here is that using virtualization, we don't usually target vulnerabilities, but we target exploitation techniques. And in this particular example, I'm going to pause it here. In this particular example, the way dirty cow works, this particular exploit works, is that it tries to modify the VDSO page in order to gain elevated privileges. So basically, if you run this exploit inside the Docker container, it will escape from the container on the host kernel. And because HVI is there and it's able to enforce read-only protection on the VDSO page at the EPT level, the exploit will fail. And as you will see on the right-hand side, and as you will see on the GitHub, for which the URL is provided in the presentation, you will see that several EPT violations are being generated, which are blocked by the hypervisor introspection, and basically the exploit fails. There is no reverse shell being generated from this exploit. So this is the first exploit that we targeted. And then we said, okay, we have one for the memory protection. How about we find one for the rather simpler case of an exploit which tries to disable SMEP, supervisory mode execution prevention. And we have one in the embodiment of CVE 2017-7308. And this particular exploit, it's not about the vulnerability in itself as much as it is about the exploitation technique. And this exploit, in order to gain code execution inside the Linux kernel, first has to disable SMAP, which is just a bit inside CR4, right? So once the exploit manages to disable that bit, it will get arbitrary code execution inside the kernel, and from within the container, it can compromise the entire Linux kernel. But because HVI and VBH can leverage virtualization, they can prevent the SMAP bit from ever being cleared from inside the hypervisor. So as we will see right here, just a second, as you can see right here, CR violation is being triggered at the hypervisor level, which is intercepted by HVI and blocked. And another exploit fails. And the trilogy will be complete with the RunC exploit, which is a fresh exploit. It specifically targets Docker. And what happens is that in certain Docker versions, the RunC file can be overwritten by an attacker, and therefore the attacker can gain host privileges. And of course, we have a movie for this as well. And this is probably going to win the Oscar. All right. So, of course, maybe you're going to ask, okay, RunC exploit, it abuses file system functionality, right? It can write inside the RunC file. And yes, that is correct. And normally, you don't need hypervisor introspection to block this. But the reason we are showing this is because we got several questions that were along the lines of, okay, you have virtualization security, what about traditional security where, for example, you want to intercept a regular API to observe the behavior of an application or the OS? And we said, no problem, you can also do this. And this is exactly what we are showing here. We are intercepting the write system call from within the hypervisor by placing a small VM call on it and filtering all the file system activity. And in this particular scenario, when the RunC exploit is being executed, we're going to block the actual write inside the RunC file, and the exploit will be prevented, right? And of course, as you can see in the video, the exploit was blocked. All right. So, in conclusions, we have demonstrated 3 attacks, 3 different types of exploits, which are particularly useful for an attacker when attempting to exploit a container. And right here you have 2 URLs, both for the VBH project and the VBH sample, which is the HVI mini project, which basically leverages the VBH API in order to provide introspection and protection for the kernel. And of course, we wish to create an ecosystem and to get people to contribute to the projects, both VBH on the one hand, the hypervisor project, and on the HVI side where the actual protection, the logic goes. Thank you. Questions?
Can you go into detail on how you're doing nested virtualization, specifically how you manage the EPT tables?
How we manage the EPTs?
Yeah, because I'm assuming you're having to do some shadow paging of the EPT tables in the VBH code. Otherwise, you're opening yourself up to an exploit where you just launch a guest to get full access to the memory space.
Do you want to take this one? Or? I'm not sure. You're asking from the perspective of the hypervisor or from the perspective of the introspection module?
The perspective that your value cell for EPT is that you can add extra protections on top of the guest kernel, but the guest kernel, if you're allowing the guest kernel, sorry, not the guest kernel, the original host kernel to launch a VM and you're not intercepting its EPT tables, it can simply launch itself as a guest to get full access to memory.
So if the guest kernel runs a VM, you're saying, if it can run a VM and get a hold of its EPT, is that what you're saying?
My question is, are you letting the host kernel configure the EPT tables for a nested guest directly?
Yeah. So I think you are asking about the coexistence, right? How does KVM does and why the KVM is running, then what kind of a mode that the rest of the kernel is running.
Yeah, are you running KVM in the VBH then?
So at this point, what we are doing is we don't want to have a nested virtualization using VBH. So we have a kind of 2 hypervisors, right? And as soon as the processor get out of the KVM, we go back to the guest mode again. So the rest of the kernel runs still in the guest mode. But when we enter the KVM, we go back to the hypervisor mode. Then KVM can just use.
How do you manage that transition?
In a way, it's similar to the address separation, the previous talk. But whenever we get out of the KVM, we turn on the virtualization, and then From there, EPT will be active.
Last question, just use a trampoline. For example, if you take an interrupt, KVM will do a direct call into the interrupt handler. How do you manage that boundary?
Yeah, that part is not closed yet. So whenever, KVM is running and then KVM handle the external interrupt, at that point, it's still in the root mode, right? Then the interrupt handler itself will be handled in root mode, hypervisor mode.
Do you then inject it back into the guest?
We could run that interrupt handler in probably in guest mode as well, but that's not done yet. Yeah.
So wouldn't it make sense for some users to also add similar interfaces to KVM? Like if you want to tell KVM don't allow clearing SMAP in CF4?
Well, actually, about that, I think we have a good presentation about that tomorrow, where we're working on some patches on KVM in order to have an API which allows potentially security module to enforce some policies for the guest VMs. Yeah.
Okay, and the second question, like the separation between two modules, why not a single one?
We try to reuse KVM as much as possible. And right now, for simplicity, it's a separate module. But in the future, it's, of course, great if we can merge. And if we can have some hypervisor that can handle both host side and then also VMs, that'd be great.
Just a quick question. Do you have plans to integrate VBH on libVMI?
So the question is if we have plans to integrate VBH with libVMI.
It's a library which has been existing since 10 years.
Zen, the library so libVMI library for virtual machine introspection, right? Which is used already on Zen and
because there's already a community which exists around this library, and
the API was inspired from libVMI. I know that for sure, but other than that, I think it's too early to say if libVMI will ever be runnable on top of that.
Okay, thank you.
No question, so thank you.
Thank you very much.